In this video, we are going to go over some of the basic concepts and theorems that we will use in doing public key cryptography. Okay, so this is a review. What we need would be some elementary number theoretical stuff, okay, including concepts and theorems. The first theorem is the fundamental theorem of arithmetic. Okay, so this just means that any integer greater than 1 can be constructed by using prime numbers. In other words, any integer greater than 1 is a product of prime numbers. Moreover, this product has a unique representation if prime numbers are listed in non-decreasing order. Okay, so this, so let me start an annotation here. Okay, so we know that, so any integer, we want to know how to build this integer. And this fundamental theorem of arithmetic says prime numbers are building blocks of all integers. In particular, this is done by you keep dividing. So for any integer, you can just find its factors, and of course, the factors will be some power of prime numbers. So this theorem just says that any integer can be written as a product of prime numbers. That's the first part. The second part is if you list prime numbers in increasing order. So this is strictly increasing order. So if n has a prime P1, maybe 2 occurrences of P1, then it would be P1 squared, right? So this alpha 1 is the exponentiation for that particular prime number, and this alpha 1 is a positive integer. So if you write n in this way, it is unique. So that is fundamental theorem of arithmetic. A prime number is an integer greater than 1 that does not have divisor less than n, okay, and greater than 1. So that is the prime number. And then we want to know how dense prime numbers are. And this theorem says that prime numbers are dense, okay? So we let pi of n be the number of prime numbers that are less than n. Then we know there are about n over log n many prime numbers in this range, right? So this range. And then how many of these are prime numbers? Then we know that there are about n over log n prime numbers in this range. Okay, so altogether there are n numbers. So that means, and also they are distributed by, so for instance, you look at a range. Say this is X, okay, and then use M. Let me use M. Let me use maybe use K. Then from K and plus log K, then you probably in this range you will have a prime number. Okay, something like that. Or maybe log N. Okay, maybe change this to log N. Log N. Then in this range there will be a prime. Okay, so that is the density of prime numbers. And it is called prime number theorem. And now we look at modular arithmetic. We have addition, subtraction, and multiplication, modular M. So modular M means you take the remainder, right? So A mod M is equal to the remainder. So this is the remainder of A divided by M. So that's A mod M. For instance, if A is 5, M is 3, so the remainder of dividing 5 by 3 is 2. So that is the remainder. So then this means we can have we can write A mod M be the quotient so let me use Q to indicate quotient of A divided by M plus the remainder. I use R to indicate the remainder divided by M. Okay, so for instance, oh, I'm sorry, that's the other way around. Sorry. So this is that. Okay, so what I'm going to try to say here is this. Okay, I'm going to say N is equal to A, right? A is equal to A divided by M. So the quotient, we can use a floor, which is the largest integer at most. Now it's an integer, but it will not exceed the value of A divided by M, and plus A mod M. Okay. So that is, you can write A in that way. So this is a remainder. This is a quotient. For instance, you can think about if A is equal to 7, M is equal to 3, then A is equal to 7 divided by 3. So taking the floor, that is 2. And then you take the remainder. So that is 1. So this is 2 times, so we should m times, okay, so we use this. So this should be m times this. So that's times 3 plus 1. So that's 7. Okay. All right. So that's one thing that you may find it useful. And for this arithmetic, modular arithmetic operation, so these are the rules. And so if A times B mod M is equal to, you put M, so distribute mod M individually, but the product of these two may still be bigger than M, so you need to take a mod M again. So let me rewrite this. A mod M times B. So this may still be greater than M, so you mod M again. Okay, so you can change this multiplication to plus and minus, that still holds. And the congruence relation defines a relation, and which is an equivalence relation. We can write it as A congruent to B mod M. And this means if and only if A minus B is divisible by M, that means if and only if A minus B mod N is equal to 0, because it's divisible. Okay, so that is these operations, and the first two are the theorems. The second two are the operations. One is the arithmetic operation. The other one is a relation, congruence relation. So now let me move to the next slide. Okay, so we talked about earlier multiplication. So the inverse of multiplication is division, but for modular operation, inverse does not always exist. Okay, so but for encryption, if we use modular product, then the inverse should be, the decryption should be inverse modular operation. So then we want to know when inverse exists. So first, we define what inverse means. Okay, so let me start annotation. Okay, so inverse really means that if, let's say, A, I want to know whether inverse of A mod n has an inverse if there exists B such that A times B is congruent to 1 mod n, which means that A times B minus 1 mod n is 0. So if this is the case, then the inverse, we say the A inverse mod n, then in this case is B. Okay. So we know that not every number, not every A or n has inverse. For instance, if A is equal to, let's say, 4, n is equal to 6, then A mod 6, okay, 4 mod 6 doesn't have inverse. The reason is that you can't find any number B such that A times B is congruent to 1 mod 6. This A is 4, so let me put 4 here. So no B such that this is true. Okay. So you can try, say, so B would be, if B is 1 is not true, right? Because 4 mod 6 is 2, and B is equal to 2, and 2 times 4 is 8. 8 mod 6 is also 2, and then B is equal to 3, and 3 times 4 is 12, and 12 mod 6 is 0, that's not 1. And then B is equal to 4, that's 16. 16 mod 6, which is 4, right? I'm sorry, 16 mod 6. Yeah, that's 4, and that's not 1. Okay, so there is no such thing to make it true. All right, so, and then what we want to know here is when this inverse exists. So this Euler theorem says that, gives you a condition, okay? This condition, in order to define this condition, let's look at Euler's torsion function. So this torsion function, first of all, we use the fundamental theorem of arithmetic. We know any number n can be written as a unique product of prime numbers. Okay, so let's write it as this, and each of these alpha is greater than or equal to 1. These p's, of course, may not be, these prime numbers may not be consecutive, okay? They just, these are written as a product of these prime numbers. And then the quotient function of n is equal to P1, so you reduce alpha 1 by 1 times P1 minus 1. So for each of these P, you do the same. So let me change this to I, then I from 1 to T. So that is quotient, Euler quotient number or function. And if n, a particular case, is a product of two prime number, then phi, okay, phi of n will be equal to, oops. Okay, let me, it's a mistake. Okay, so then phi of n, so this Greek letter is pronounced phi. So this will be equal to p minus 1 times q minus 1. So we are going to use this in our essay. Okay, so later on. All right, so once we define this phi of n, then Euler's theorem says the following. So given A and n, I want to know whether A inverse mod n exists or not. We'll say this exists if GCD AN is equal to 1. So that means the greatest common divisor of A and n is 1. In other words, A is relatively prime to n. And not only we know it exists, we also know the form. The form is A to the phi of n is congruent to 1 mod n. So that means, i.e., I'm gonna put it down here. A inverse mod n is equal to A phi to the phi of n minus 1 mod n. Okay, so that's your B. So this is your B. Okay, so that is Euler's theorem. Now let me erase this. So we see a special case of Euler's theorem is when n itself is a prime number. Then in this case, Euler's torsion function of P is just P minus 1. So that means if GCD AP is 1, then we know A to the P minus 1 is congruent to 1 mod P. And this is called Fermat's-Little theorem. So in this case, we know the A inverse mod P is equal to A to the P minus 2 mod P. Okay, so that now we know when A modular inverse of A mod n exists. Okay, so we will need to use this result when in RSA cryptography or public key cryptography. We're going to use this quite a bit. Okay, I'm gonna remove this before I go to the next slide. Okay, so I'm clean. Okay, the next slide is primitive roots. So this is a concept. This concept is used in Diffie-Hellman key exchange and some other operations. Okay, so what it means is this. So we know if GCD AN is 1, then by Euler's theorem, we have a to the phi of n is congruent to 1 by n. So so that we know, okay? The second bullet, so if a to the m's power by n is not congruent to 1 by n for m less than phi of n, then a is a primitive root. Okay, so primitive roots exist. Exists for certain n, okay, but not every integer n has a primitive root. Okay, so now let me erase this, and we look at a very useful algorithm that's called fast exponentiation, fast modular exponentiation. So we are going to use this a lot for encryption and decryption, and also for Diffie-Hellman key exchange. So this is used in Diffie-Hellman key exchange and RSA encryption and decryption. Actually, the encryption and decryption for RSA is the same, are the same. Okay. All right. So now let's see, how do we? So let me open up a whiteboard. Okay, so what we want to do is to compute a to the m by n. We want to compute this fast. So we want to compute this fast. Okay, so if you use a naive algorithm, that would be you first. So this you first multiply a to the m. Sorry, multiply a for this many times. Right, so, but then of course, this is a huge number. This could be huge, and it's costly, time costly. Okay, but if you look at the result, now no matter how big this one is, the result is always less than. The result will always be less than n because you take the modular operation. So that means that we can find a fast algorithm of computing a to the m by n. So the first thing we want to see here is assuming m is a power of, let's say m is a power of k. For some k, then a to the m by n then is equal to a to the 2 to the k by n. And this then can be written as a squared n squared n, and you keep squaring. Okay, and then n. So you do k times of squaring. So which means you only incur k multiplications, okay, because the squaring just multiplication of a number less than n, because each of these numbers is less than n, you have a modular, and then you take the modular operation. So there's at most 2 to the k operations, okay, and k here is just log m, okay, with base 2. So it is a much fast algorithm doing this way. So this is a special case. What happened is that m is not power of 2. So that means now we'll first write, so in general, write m in 2 binary. That means m is equal to summation so let me so with that, so it would be like this, b k 2 to the k bk minus 1 2 to the k minus 1 b1 2 plus b0, where each of these bi is either 0 or 1. Okay, and of course bk is 1, but some of these may not be. So that means I can also write it as 2 to the I when bi is 1. When bi is 0, so that term disappears. So with this, then we know, so with this we know that a to the m not n is equal to a to the bi1 to the I not n. Okay, so that can be written as a product, okay, a, so that's 2 to the I, oh, sorry, that can be written as yeah, so a product a and then 2 to the I for bi, which is equal to 1. Okay, so now for each of these terms, we have come down to this special case, right? So that's the idea of a fast, so that is the, so then we can use this fast exponentiation to do each of these and then multiply them back, okay? But we can even do, we can do even better. Okay, so for this, you still, for each of these is at most 2k operation, and then you multiply them back, that's at most k, so there's a 3k operation, right? This is at most 3k at most, but we can do much better. So, and we can reduce this 3 to 2. So now let's see. Let's go back. Okay, to the algorithm. So the algorithm is this. So we first let k, so this k just be log m with base 2. And so in this slide, I use x as m. So here, m is equal to x. Okay, so then we'll start with gk, which is a. And then I will let this index I to go from k minus 1 down to 0, because bk is always 1. Okay, so we will just need to figure out the rest of the bi, right? Okay, so first, so this I will always be a square of the previous. Okay, gi will be the square of the previous g, so that's gi plus 1. And then we are going to check now. So for this part, will always just be the case that when the exponent is the power of 2. But so when we cross a term, so that means when bi is equal to 1, then we have to multiply gi with a and mod n. And then g0 would be the result. So now let's look at an example. To help you get used to this idea. Okay, so let me just start a whiteboard. Okay, start a whiteboard. So let's say, let me let A be 4. Let's say M be 19 and N be 5. So I want to compute 4 to the 19 mod 5. All right, so first we are going to convert 19. So this is decimal into binary. So the arithmetic for doing so is this. So it's 19. We first divided by 2. So that's 9. So we got a remainder 1, right? Because 2, 9 is 18. We got remainder. So we keep doing this. So got remainder 1. 2, 4 is 8, right? And then 2, 2, that's 4. So the remainder is 0. And then do it again. So 2, 1. So the remainder now is 0. Okay, so 19. So we work our way back. So this is the most significant bit. Because it has I have done this division of 2, okay, many times. So this is the most significant bit. So that's 1, 0, 0, 1, 1. So that's binary. And you can verify this, right? So this is 2 to the 4. So this is 2 to the 1 plus this is just 1. So this is 16 plus 3 plus 1, that's 19. Okay, so then 4 to the 19 mod 5 would then be equal to 4. We know this is 2 to the 4 plus 2 plus 1 mod 5. Then this is equal to 4 to the 4 times 4, 2 times 4 mod 5, and it can be written as 4 to the 2 to the 3, 4. So we get square here, 4 mod 5. All right, now the algorithm is to keep squaring the previous number. So now we know G5. Okay, so look at this number. So this is, so K is equal to 4 here. Okay, so this will be G4, right? So we know B4 is 1, B3 is 0, B2 is 0, B1 is 1, B0 is 1. So these are the binary bits. So this will be 4. So that will be 4. And then G3 will be 4 squared mod 5. So that is 1, right? So 4 times 4 is 16. 16 divided by 5 is the remainder of 1. Okay, and then B3 is not 1. So I'm going to do G2. Which will be G3 squared mod 5. G3 is 1, so that is just 1. So it's very simple, right? And then B2 is 0, so we are going to do this B1. Oh, sorry, this is G2. This is G2, so it will be, so this is G1. So it will be just G2 squared mod 5. Again, this is 1. Simple. Now, B1 now is 1. So what we do is that when we get G0, well, first we get G1 squared. I'm sorry, G1 is not 0 yet, okay? So let me undo. This time I need to multiply G1 with 4 and mod 5. G1 is 1, so then this is equal to 4. Okay. Okay, now then I'm going to compute G0, which is G1 squared mod 5. So again, this is equal to 1. Okay, this is the same. But then we also know E0 is 1. So then G0 will be equal to G0 times 4 mod 5, and this is 4. So the result then is 4. So this is the result. Okay, so now let's go back to the next slide. So it's finding large prime numbers, because we will need in RSA or in Diffie-Hellman, we will need to find large number prime numbers. We are going so. Right now, the state of the art is that there is a deterministic algorithm to determine whether a given odd number is a prime number. Okay, but the most efficient way to determine whether a odd number is a prime is to use Wheeler-Rabin's primality test. Okay, so this is very efficient and with a very, very small probability of error. So this is a probabilistic algorithm. This is not a deterministic algorithm. So the idea is this. So let me start an animation. So we have a number n. So let's say n is odd number, because a prime number has to be odd when it's big, right? So there's only one even prime number, that's 2. Okay, so any other prime number is odd. So given a n, which is odd, I want to know whether that n is a prime number. So this test runs as follows. So the n, so we want, let's say, so the n minus 1 will be even, and then, so because it's even, you will have factor of 2, so you'll keep getting factor of 2. Let's say you have k copies of 2 as a factor of n minus 1, and then times q. So this test will be, I'm going to choose a random and integer a is between 1 and n minus 1. Now remember, if n is a prime number, then by Fermat's-Little theorem, then we have a to the n minus 1, which is congruent to 1 mod n, if n is prime. Okay, so this test is based on this. So what you do is you try to see, oh, this should be n. This should be n. Okay, so you run you run this test. See whether a to the q's power mod n is not equal to 1, and a to the 2 to the j's power times q's mod n is not equal to -1 for all j. Okay, if this is true, then we'll say n is not a prime, because when n is a prime, it should have this. Otherwise, we'll output n is likely to be prime. Okay. So then you choose another random number, you do this again. So if you run enough number of primes, or turns out like this n is likely to be prime, then this n, then we'll say that n is a prime number. Okay, so this is the Miller-Rabin's primatic test. All right, so that's what we need when we talk about RSA and and this is what we need in RSA and Diffie-Hellman key exchange and some other cryptography stuff. Okay, so let me stop here.